So, yeah, I did. So, those pictures you saw flashing by in the beginning, those are images related to the golden ratio, and this came up in CSE 215 the other day. Um, Golden ratio is about 1.6 something. It's a number that pops up all over the place. It pops up in music and in art and in nature. And even if you don't know anything about the golden ratio, you certainly encountered it, probably multiple times. Yeah, I'm playing with weight screens because why not? And the golden ratio is related to something called the Fibonacci series, which a number of people are familiar with, and we've talked about it in 215 also. But I want to start off by looking at Fibonacci sequence. And we're doing this for a couple of reasons. One, because this is a recursive sequence that we can define, with a recursive relationship. But two, because computationally it gets us into some interesting aspects. So let me start off by just kind of reviewing the Fibonacci sequence. And so this is a sequence that we can easily write by hand by just starting with a pair of ones and then writing down the sum of the two previous terms in the sequence. So 1 plus 1 is 2, 1 plus 2 is 3, 2 and 3 is 5, 8, 13, 21, 34, 55, and so on. And it's a sequence of numbers that pops up a lot of places. For example, in counting the number of petals on a flower, or the number of seeds in the spiral of a sunflower, and seeing how that grows as you move outward. And it's got lots of interesting properties in itself. If I take 5 squared, that's 25. If I take 3 times 8, that's 24. 8 squared is 64, 5 times 13 is 65. The square of any number is always plus or minus 1, within plus or minus 1 of the product of the numbers before and after. The ratio of each number to the number before it approaches the golden ratio. It's 1.6 something, right? And so this is related to that ratio, and that ratio has to do with proportions and certain symmetry relationships in proportions. So this is a cool sequence, right? It was, developed in the study of populations. It pops up in nature all over the place. If you look in bee colony, the population of females to males is the golden ratio. It comes up all over the place. It's interesting for us in this part of the course because we can define what's called a recurrence relation, which says the nth Fibonacci number is simply the sum of the two Fibonacci numbers before it. Now, we don't need to do this to calculate Fibonacci numbers. We can simply, keep track of, previous and current, and then set, a new current equal to previous plus current, and set previous equal to whatever that previous current was, and just do this in a loop, right? And that's very efficient. But since we're doing recursion, we're doing trees which are recursive, we can define fn in terms of, earlier values of f. So fn minus 1 and fn minus 2. But we need a base case, right? If we try to use this to find f5, we'll say it's f4 plus f3, that's fine. If we try to find f1, it's going to say f0 plus f minus 1, which doesn't make any sense. And f minus 1 would be f minus 2 plus f minus 3, and those don't make sense. So we need to chop this thing off. And so we're going to set this equal to 1 if n is less than or equal to 1, and it's going to be this recurrence relation if n is bigger than or equal to 2. Right, so the first two terms if we start, you know, from F0, F1 would be 1, and then F2 on up would be this recurrence relation. So this is, you know, our base case inductive step from 215, and we can prove that this generates the Fibonacci sequence using an inductive proof, right? This would be our base case, and this would be our inductive step. So we can do all that, but let's code this up, okay? Let's look at some code for this. And it's a pretty short function, right? And it comes straight out of the recursive formula. So if our argument is less than or equal to 1, we're just going to return 1. Okay, that's our base case. And then our recursive step is just return the sum of the two previous values. So I'll calculate fib I minus 1, I minus 2, set those equal to answer, and return my answer. So that's a really simple function to write, and we can exercise it by just making a loop. So we'll go from 0 to 45, we'll calculate the ith Fibonacci number, print out the result. And this works, right? You can see our first few numbers are what we got by hand. But what's surprising is how slow this is. Right, so it's working on fib 44 right now, and it's taking it quite a bit of time. And you know, we could add these two numbers together by hand to find the 45th Fibonacci number, but it's taking it a really long time. It's clearly doing something more than just adding these two integers together to get this. Now it gets the same result as if it simply added these, but that took a lot of CPU time. So what's going on in here? Well, here's a modified version of that previous function, and I've added one extra line in here. I increment an evil global called count, which I initialize to 0 before I call the Fibonacci function in my main program. So I initialize count to 0, and then every time I go into fib, I increment. And when I come back from my call to fib, I'll print out not only the answer, but the count of how many calls were made to the Fibonacci function. And what you see here is that not only are the Fibonacci numbers increasing, but the number of calls it takes to calculate an nth Fibonacci number is also increasing. And the number of calls looks something like a Fibonacci sequence, right? 3 plus 5 is 8, while to calculate the next Fibonacci number it took 9 calls. 15 and 25 is 40, and to calculate the next Fibonacci number it took 41 calls. And so the amount of work that's going into calculating the 46th Fibonacci number will be, you know, some huge number of calls to the Fibonacci function. And that kind of makes sense. So let's look at this. Let's see what Fibonacci 10 is. And to calculate F10, we need to calculate F9 and F8. And to calculate F9, we need to calculate F8 and F7. And to calculate F8, we need F7 and F6. And so on. Now eventually we'll ask for F2, which will be F1 and F0. And these two calls won't recurse. Those will hit our base case where our argument is less than or equal to 1, and they'll just return 1 right away. But up here, to calculate F7, we need to calculate F6 and F5. And to calculate F6, we need to calculate F5 and F4, and F5 takes F4 and F3, and so on. And this F5 over here takes F4 and F3, and so on. And all of that will get us F9. And then to do F8, we'll have to do F7 and F6, and F7 will require F6 and F5, and so on. And the total amount of work that we're doing to find F10 is basically, you know, the number of recursive calls we have to make to find F9, plus the number of recursive calls we have to make to find F8. And so the value of the nth Fibonacci number is actually, you know, covertly encoded in the amount of work that the CPU has to do. So you could measure, you know, the amount of energy being pulled from the wall during this calculation, and I don't even need the return value from this function. I could calculate the Fibonacci number by the amount of work that was done, the amount of heat that was generated, the amount of time that passed. So covert channels in nature. But anyway, here's the thing, right? This is not tractable. This is not going to, you know, calculate the 100th Fibonacci number by the time class is done. Probably by the time the quarter is done. Probably by the time you graduate. It's not going to get there, right? It's roughly doubling. Well, it's going up by 1.6 every time. So we'll save my CPU. But the thing to observe is that, you know, to calculate F10, I need to calculate F9 and F8. Well, in the process of calculating F9, I'm going to calculate F8. Which means when I come back from this calculation, I don't need to do all of these recursive calls. I can prune that part of my tree. If I have a way to save the value of F8 when I calculated it. And to calculate F8, I'm going to need F7 and F6. Well, if I save the values of these once I calculate them, when I come back here, I won't have to do any of these things to calculate F7. So we're going to cache our results. And this is something called dynamic programming. And yeah, in this case, it's going to be a straight calculation down the left side of the tree. Now that's not always the case with recursive functions. But for Fibonacci sequence, it actually works out that way. Which means we could actually just start from F1 and run up the tree in this direction. But don't be lulled into thinking that you can always do that, because often you'll end up doing more work than you need. But basically, the first time you calculate F5, that's the only time you're going to calculate F5. Any other calls to it are going to get pruned out. So what we need to do is we need a way to save the results of our calculations so that the next time we ask for the same value of our function, we don't repeat the work. So I'm going to do almost exactly the same thing we did in our original function, but I'm going to add one additional line. So I'm going to make another global. This is going to be an array which acts as my cache. So I'm calling this save, and it's going to hold 1,000 elements, and I'm going to initialize those to 0. Because I know my Fibonacci numbers are never equal to 0. So I'll initialize these to 0. And then I'm going to do two extra things in my Fibonacci function. The first thing is when I'm asked to calculate fib I, before I do any of the recursion, I'm going to check my cache. I'm going to check my save array and see if element I is non-zero. If it is, then I must have saved a result in there, which means that value of save I is the value of the ith Fibonacci number. So I'm just going to return that. I'm going to skip all the recursion. But if that element in the cache is equal to 0, that's the initial value. It means nothing has written a value in there. I've got no choice. I've got to make my recursive calls, calculate fib I minus 1, I minus 2, add them together. But the other thing I'm going to do is before I exit, I'm just going to save that in my cache. So dynamic programming is really just adding something in the beginning and something at the end of your time-intensive function. At the end, after you've calculated your answer and potentially spent a large amount of effort finding that, save it in your cache. And in the beginning, before you do any hard work, see if you've already saved an answer in your cache. So these two steps go together. They're not complex, right? But they've got to work together. And if you don't understand the goal here, right, then you can write lots of things that look like this but don't actually cache your results. So it's easier to start from the end. Here, once we found our answer, let's save it in our array. And here in the beginning, before we calculate our answer, see if we've already saved it in our array. And if we have, just return it from the array. And so if we do this, right, our function runs very quickly. So there's the first 1,000 Fibonacci numbers. And the numbers aren't correct because, you know, a long int isn't big enough to store most of these Fibonacci numbers. But, you know, it clearly gets through way beyond the place where we were before. And it takes almost no time. And you can see the total number of calls being made to the Fibonacci function is 3. So we've curtailed that deep recursion, and that's where our time was going. And this will work up to, looks like the 91st Fibonacci number is fine. And then the sum of these two numbers is bigger than we can put in a long, so it rolls over and becomes negative. Yeah, I had a long for big ints. I could probably make it unsigned and squeeze one more iteration out, you're right. Looks like I could squeeze, yeah, one more and then it'll roll over again. Alright, so that's the idea of dynamic programming. We're going to cache our results so that we don't have to always do the full recursion. Alright. And so we're going to use this to look at the maximum value function, which is the algorithm that you're implementing for your knapsack problem for PA5. And so let me rehash what that algorithm looks like. So we're finding the max value of a bag with some capacity. And it's going to be the largest of the following. The value of the first item in our inventory of items, which is what we get out of our bag if we start by putting in item 0. We get the value of item 0. And then the holding capacity of our bag decreases by the weight of item 0. So we have capacity minus weight of item 0. That's how much capacity we have left in the bag. And what's the most we can get out of that? It's just max val of that number. If we start by putting in the second item in our bag, we get that much value, the value of that item, plus whatever the remaining capacity allows us to put in our bag. That's what the maxval function will tell us if we call it with an argument which is the original capacity of the bag diminished by the weight of that second item. And we can go up, if we have n plus 1 items, it'll be the value of the n plus first item plus max val of our original bag's capacity minus the weight of that item. And whichever one of these is largest, that's the maximum value we can get from our original bag. So this was the algorithm we went over yesterday. And you know, you need to make a loop and you need to do something to find the largest of these. Don't calculate them all and save them somewhere. Well, I mean, you could do that, but you know, start off with the value of this and then calculate each of these, compare it to the maximum value you found. And if this is bigger, then this is your new maximum. Keep calculating. If you find another one that's bigger, then that's your new maximum. When you get through your whole loop, you know what the maximum value is. And that's the max val for this capacity. And there's two details here. The first one is if the item, you know, if item 1 weighs more than the capacity of our bag, we're not allowed to consider this. This is the value we get if we start off by putting item 1 in our bag. But if item 1 weighs more than our bag can hold, then we cannot extract this value, whatever this turns out to be. Right? So as you're going through your loop, make sure that you're only considering items where the weight is not bigger than the capacity. We also need a base case so we don't recurse forever, and the base case is if our capacity is 0, return a 0. You can't store anything in the bag. There's nothing that has any value. Don't ever call max val with a negative number. it probably means you're doing something wrong. So you could put a check in here if capacity is less than 0, halt and catch fire or something. All right. The other issue, and this is the one we left off with yesterday, is that in addition to knowing what the maximum value is you can get from a bag, we want to know how many of each item we should use, how many we should put in our bag to get that maximum value. So we want to know an item count that maximizes the value that we get out of our bag. Which means we need to know more than just the integer maxval that comes back. We're going to need an inventory. So what I want to do is I want to work through an example in gory detail with a particular set of items, and I want to see how this works. And this will illustrate our caching of results for dynamic programming, but also how we record the inventory of items that gets us a particular maxval. All right, and I'm going to start with 3 items. I'm going to call them item 1, item 2, and item 3, and I'm going to record their value and their weight. And so item 1 will be worth $2 and will weigh 1 ounce, so that's the pencil. Item 2 will cost $9 and weigh 3 ounces, and that's the expensive candy bar. And item 3 will be worth $13 and weigh 4 ounces, and that's the fancy notebook. And remember, a greedy algorithm doesn't work here, right? A greedy algorithm would say, look at your most valuable item per weight. And this is worth 3 1/4 per ounce. This is worth 3. This is worth 2. Since this is the most valuable item, a greedy algorithm would say, put in as many of item 3 as you can. And when you can't fit any more, put in as many of item 2 as you can, because that's the next most valuable. And when you can't fit any more, put in item 1 for the rest. And that does not get you an optimal solution in all cases. And the example we saw yesterday, which we'll come back to today, was capacity is 6. So if we take our greedy approach, this is the most valuable item, so we'll put in item 3, which weighs 4 ounces and is worth $13. That leaves us 2 ounces of holding capacity. We can't put in any item 2, but we could put in 2 of item 1. So we can put in item 1, which weighs 1 ounce and is worth $2. And we could put in 1 more, which is 1 ounce and weighs $2. And that gets us $17. The better solution is to put in item 2, put in 2 of those. Those each weigh 3 ounces and are worth $9 and gets us a total value of 18. So it's not greedy in the sense that we have to circumvent what would look like our best bet. This is the most valuable item. We deliberately do not put that in our bag. We start by putting in a less valuable item, but in the end, we end up maximizing our total amount of money. I don't know if there's a name for an algorithm that's not greedy. You hear algorithms referred to as greedy algorithms, but there's other types of algorithms, and if it's one of these other types, then it's not greedy. But yeah, we could call it not greedy. And yeah, there probably is a notion of levels of greediness, because there's problems that you can't solve where you're guaranteed to get the best solution, but you can approach the best solution within some percentage or some probability. And those might, use degrees of greediness along the way. And you can look at things like simulated annealing, for example, which is kind of a bit of a greedy thing, I think, that approaches a good solution but isn't guaranteed. Or the stingy algorithm, there we go. And so, yeah, when we're looping through, if we find that the 2 or more of these give us the same maximum value, we can choose either one. And it will give us the same maximum value at the end, but it may give us a different inventory of items that gets us there. But we can choose any one that we want. And depending on how you code your loop that looks for the maximum value, you may end up picking one or a different one. So yeah, something like linear programming. All right, so we're going to do a very detailed example of the maximum value function. This is where you really want to be tuned in and paying attention, because if you look up in 5 minutes, none of this is going to make any sense. So we're going to work through this, and we're going to try to calculate the maximum value of 10. We're not going to go all the way through 10, but I'll start with 10 just to see kind of what's involved, but we'll stop when we find max val of 6. So here's my program / computer memory, right? This is my max val function. And when I call max val with 10, I'm going to, create one of these. So this is like, the memory of the computer for calculating the max val function. And I've called it with a capacity of 10. And the goal is this function should report what the maximum value is for a bag with this capacity and what the item count is that gets us that maximum value. So our main program is going to call maxval 10. All right, so it's going to make a call to this function, which says, okay, I've been called, my capacity is 10. How am I going to find what the max val is? And since there's 3 items, it's going to do 3 calculations. Okay, the first calculation, we'll do these slowly to begin with, and then we'll speed up. The first calculation says I could begin by putting item 1 in my bag. And if I do that, I've got $2 of value already, because item 1 has a value of 2. Item 1 also weighs 1 ounce, which means while my original bag could hold 10 ounces, my remaining capacity is only 9 ounces. Now, what's the most amount of money I can get by putting items into a bag with 9 ounces? I don't know. But if I call maxval with an argument of 9, it will tell me the answer. And it's also going to tell me what the collection is of items that I should use to get that maximum value. All right, so this is going to make a recursive call to maxval of 9. So let's go ahead and do that. So I'm going to call maxval 9, which means all of this is going to go away. Where's it going to go? It's going to go on the stack. My 10, my 2, my 9, the fact that I'm doing this first calculation, all of that gets saved on the stack. And now the CPU just says, hey, I'm going to calculate max val of 9. All right, well, how can I do that? Well, let's see. I could start with item 1, which has a value of 2, and reduces my capacity by 1, so I need to find max val of 8. Okay, it's going to make a recursive call to max val 8. So this goes on the stack. And the CPU says, oh, I guess my life is calculating max val of 8. And I could do that by starting with item 1, which has a value of 2, and then add max val of 7. So it's going to make a recursive call to max val 7. So this goes on the stack. And we call max val 7. And it says, well, I could start off with 2 plus max val of 6. All right, so you get the idea, right? So max val 6 is going to calculate 2 plus max val 5. And max val 5 will calculate 2 plus max val 4. And on and on and on. Max val 4 will be 2 plus max val 3. Three will be 2 plus max val 2. Max val of 2 will be 2 plus max val of 1. And max val of 1 will be 2 plus max val of 0. Okay, when I make a call to max val of 0, we're not going to recurse. That's going to be a base case. If your capacity is 0, then your max val is equal to 0. So this is going to be calculated without doing any recursion. It's going to be an if statement in the very beginning. And we're also going to report the inventory that you use to get this maximum value is to take none of items 1, 2, or 3. And yeah, our stack is pretty big right now, right? The stack grows dynamically on most systems. And it will basically grow until you run out of memory, at least memory in the stack area. And when you run out of stack space, that's a stack overflow, and that's usually a really bad situation going on. And so at the very least, your program will crash, but depending on the system, the whole system could crash. What if you can never logically get to 0? So if you don't get to 0, then you're going to recurse forever, and you're going to run out of stack space, or pieces of paper in this case. But yeah, you would set your base case to something that you're more or less guaranteed to encounter. And we're going to see another situation where we ignore certain cases here. So ultimately, your recursion has to end. It may end because you call a base case, but it may simply end because we decide not to make any more recursive calls. And we'll see an example of that in a couple of minutes, which will make more sense. All right, so we can return from our recursive call to maxval 0, and now we can perform this calculation. So what did maxval 0 do? It told us that the maximum value is 0 and the inventory is 0. And so now we can calculate 2 plus maxval of 0 is 2. Okay, now capacity is 1. We could also say that if we start off by putting in item 2, we would get a value of 9 plus the maximum value of 1 minus the weight of that is minus 2. Well, that's not a valid calculation, right? Our capacity is 1 and item 2 weighs more than that, so we're not allowed to calculate what we get by putting in item 2. And similarly, if we put in item 3, we would get 13 plus we take away 4 from our capacity, it will be maxval of minus 3. That's not a valid calculation either, so we're not allowed to consider putting in item 3. So our whole calculation for maxval 1 is simply finding what do we get by starting off with item 1 in our bag. So this is the formula that will give us our final answer for maxval 1, which is going to be 2. And our final inventory will be the inventory that we got by calling maxval 0. But, and here's the key part, right? Right, so this is the inventory adjustment. Maxval of 0 returned this item count. We're getting our maxval of 1 by adding 1 of item 1. So we're going to bump up the count of item 1 by 1. So this is going to change from a 0 to a 1. Okay, and that's the key point to keeping track of the inventory. Okay, we'll do that again a few more times if you missed it. But we got back an inventory of items to get maxval of 0. Since we decided starting off with item 1 gives us our maxval of 1, we take that inventory and we simply bump up the count of item 1 from 0 to 1. Okay, now we return from that call. We've calculated maxval of 1 was 2, and the inventory that gets us that is maxval of 1 is 2, and the inventory that gets us that is 1, 0, 0. Okay, which means that if we start with item 1, we get 2 plus maxval of 1 is 2. So 2 plus 2 is 4. And again, if we start with item 2, we get 9 plus maxval of minus 1. That's not a valid consideration, and item 3 will not be valid either. Items 2 and 3 weigh more than the capacity of our bag. So the maximum of our calculations will be exactly 4. It comes from this case. And the inventory that gets us that is the inventory that got us our maxval of 1, but we're going to increment the count of item 1. So this will go from a 1 to a 2. All right, everybody still with me on this? So this is the result of calling maxval 2. We're told the maximum value is 4, and you get that with 2 of item 1 and none of items 2 or 3. And you can see that works, right? Item 1 is worth 2. If we have 2 of those, that's worth 4, and that will weigh exactly 2 ounces, which was our full capacity. All right, now we return from here. We found out what max val of 2 is. Max val of 2 is equal to 4, and the inventory count that gets us that is 200. Now we can continue our calculation of max val 3, which was what this call frame was doing. So max val 3, we could also start off by adding item 2, which gets us $9 and diminishes our capacity by 3. So it gets us 9 plus max val of 0. All right, we try to calculate max val of 0. That's a base case. Max val of 0 is 0, and we don't get any items. And so now we can calculate these values. 2 plus max val of 2 is 4, plus 2 is 6. 9 plus max val of 0 is 9. And which one gets us our largest value? And this one we're not allowed to consider, because item 3 weighs 4, that's more than our capacity. So we only have two options, 6 or 9. 9 is our biggest value. That's our max val of 3. And what's the item count that gets us that? Well, the item count that we use to get max val of 0, but we bump up the count of item 2, so this becomes a 1. Okay, that's the trick right there. That's your final 15 points of PA5, is getting the item count that gives you the maximum value. So as you're calculating your potential maximum values, you're also getting the inventory that corresponds to this recursive call to max val. Whichever one you end up keeping as the largest, take that corresponding inventory and bump up by 1 the count of whichever item that case corresponds to. So hard to say in words. It's easier to code this than it is to describe it, right? Seriously, if you have a for loop and you're using I to iterate through your counts, and you found that you know, a value of 2, you know, I equals 2 gives you the largest one, you're just going to bump up the count of item 2 in your inventory. Just increment it. I don't know what to do with that comment when MV equals 0, increase the inventory. I don't know if that's always true. That happened in the previous case, but I think it's more general than that. When you find the item that gives you the largest value, bump up the count of that item in the inventory that you got in your recursive call to max val. We'll do this a few more times. We'll do this at least 3 more times. All right, so we found the value of max val 3. It was 9, and the inventory count was 010. That's okay. We're going to do this going forward also, right? So that's the nice thing about recursion. We can forget how we got all the previous stuff. We can start from any starting point. So let's find max val of 4. That's our whole purpose in life right now. What's max val 4? Well, it could be 2 plus max val 3. What is max val 3? Well, I've saved that in my cache, right? So this is also, you know, my cached array. I'm not going to do my recursion. I've saved the fact that max val of 3 is equal to 9, and the item counts of 0, 1, 0 give me that maximum value. All right, I could also start off by putting item 2 in my bag, which has a value of 9 and leaves me a capacity of 1. And so I need to find what max val of 1 is. And let me fill in these, and then we'll go ahead and we'll fill in the max val calls. The third possibility is I could start with item 3, which has a value of 13. And since that weighs 4 ounces, that leaves me a capacity of 0. And so one of these 3 cases will give me the maximum value I can get from a bag that holds 4 ounces. All right, so what is max val 1? Well, presumably I've saved that when I calculated it. And for a capacity of 1, my maximum value was 2, and the way I get that was 1 of item 1 and none of items 2 or 0. And max val 0, I can go back in my cache, but I remember its value is 0. And there's no items. So what are the actual numbers I get here? 2 plus 9 is 11. 9 plus 2 is 11. 13 plus 0 is 13. So which one gives me the maximum value? This one, where I start with item 3. Okay, so the value I'm going to return as my max val is the largest of these, which is 13. The inventory I'm going to return is this inventory, where I've bumped up the count of item 3 by 1. So I'm going to return 0, 0, 1. So this item list is fixed for the whole problem, but the inventory that gets you this maximum value will depend on the maximum value. If I'm trying to find max val 3, I get it by taking 1 of item 2. Max val 1, I get by taking 1 of item 1. Max val 0, I get by taking none of any items. But this solution corresponds to whatever you do to get max val of 0 plus 1 more of item 3. So I can take that item count for max val of 0 and I can bump up the count of item 3. So here's my final inventory that gets me my maximum value of 13 from a bag that holds 4 ounces. We can assume that there are no more than 128 items in our inventory. So we can statically allocate this cash for saving our results. That makes life easier. Alright, let's find max val 5. 2 plus max val 4. Or we could start with item 2, which gets us 9. And then our capacity of 5 is diminished by 3, so this is max val 2. Or we could start with item 3, which is 13, diminishes our capacity by 4, so it's max val of 1. So one of these 3 values will be our maximum value for capacity 5. Right, so the inventory associated with the max val n gets stored in the cache, along with the value of max val n. Alright, so let's go through our cache. Max val of 4 is 13, and the inventory for that is 0, 0, 1. Max val of 2 is 4, and the inventory for that is 2, 0, 0. And max val of 1 is 2, and the inventory is 1, 0, 0. And all of these recursive calls now are just effectively going to do just lookups in your cache. Just pulling out of an array of integers and inventories. Okay, so we can do the calculations. 2 plus 13 is 15. 9 plus 4 is 13. 13 and 2 is 15. We've got 2 ways that we can find the largest value of 15. I'm just going to start off with the first one. Makes no difference as to what the final maximum value was. Could make a difference for the inventory, but the final value will be the same. So I'm going to say maximum value is 15. And the inventory is the inventory that got me my max value here, plus I'm going to increment the count of item 1. So this is going to be 1, 0, 1. Alright, so here's our last step. This is the call to max val 6. And we can calculate our max val as being the largest of either 2 plus max val 5, or if we start with item 2, we get a value of 9. We use up 3 ounces, so it's max val 3. Or if we start with item 3, we get a value of 13. We use up 4 ounces, so we have max val of 2. So we need to calculate these max vals, which we would do with recursive calls to max val, which in all 3 cases will simply look up these results in our cache and return them. So max val of 5 is 15, and the inventory is 1, 0, 1. Max val of 3 will be equal to 9. And the inventory is 0, 1, 0. And max val of 2 is 4. And the inventory is 2, 0, 0. And the rest of the calculations, so in this case, 2 plus maxval 5, 2 plus 15, this is 17. 9 plus maxval 3 is 9, this is 18. And 13 plus maxval 2, 4 is 17. And so 17, 18, 17, this is our largest maxval. So maxval 6 will be 18. And the item count that gets us this is the item count that got us our maxval of 3. And we're going to increment the count of item 2. So instead of 0, 1, 0, this is going to be 0, 2, 0. And that's the return from a call to maxval 6. And what that tells us is if our bag holds 6 ounces, the most we can get is $18. And we can do that by putting in 2 of item 2 and none of items 1 or 3. Right? And that was the solution that we found by hand, by kind of trial and error. 2 of item 2 gets you a value of 18, and that's your best solution. All right, now you could keep doing this. You can keep unwinding your recursive call stack and basically pulling off these values from previous calls to maxval, figuring out what the largest, result of this calculation is, adjusting the inventory. That'll tell me maxval 7, and then I can use that to find 8, and that to find 9, and that to find 10. But that's the whole algorithm, right? And your goal right now, I think, is make sure you understand the algorithm. Don't be writing code yet, right? Do this on paper, do it on whiteboard. Talk to people about this. You can totally collaborate on the algorithm itself. You can totally compare notes, you can chat in Discord, you can do whatever you want with other people in the class as far as, trying to understand how this is supposed to work. And once you understand all of this business, right, then you can start writing code. And the code is relatively easy. There's no dynamic memory, there's no linked list, there's no trees, there's none of this weird stuff we've been doing other than recursion, right? But you probably wanted to make your own data structure, right, a struct, that will let you do things like, record an integer for a maxval and record an array of integers for how many of each item you want, and use that structure as the return value from your maxval function. So maxval doesn't just return an int, it returns a structure that contains an int and a list of item counts. And your item counts is really just an array. 128 items, so make an array of 128 integers, initialize it to 0, and let the ith element tell you the number of elements, number of item I that you want to get your maxval. Cool. Yeah, it takes some chewing. So here, I just made a sample file with items of this characteristics. So weight of 2, value 1, value 2, weight 1, value 9, weight 3, value 13, weight 4. And if I have a capacity of 6, right, it tells me the best possible value I can get is 18, which I get by putting 2 of item 1. If I have a capacity of 10, my best possible value is 31, which I get by putting in 1 book and 2 pens. And again, it's not greedy, right? The book is most valuable. We could fit 2 books into our bag. They only weigh 4 ounces. Our bag holds 10. We could put in 2 books. That would give us a value of 26 and would leave us 2 ounces to play with, which would let us put in 2 pencils. That would almost get us a total value of 30. So don't try to circumvent all of this and just, find the most valuable item and put in as many of that as you can and so on. You won't get you won't get an optimal solution. Right? So this takes chewing, but do something in whatever form makes sense to you, similar to what we've been doing here, right? Work through the algorithm. This is, a fine example. You can come up with examples on your own if you want. But work through the algorithm. Figure out what you need the code to do before you start trying to write the code. Right? And if you can do this on paper, you can write code to do it. Okay? Everybody here is at that level. If you can do this on paper, you can write code to do it. But you got to know what you're trying to do on paper first, and then translate that into C. All right, we are out of time. Play around with that, chew on it, come to office hours with questions. Enjoy the afternoon, and I will see you tomorrow.